My name's Will Matthews,
I'm Hope Poen.
I'm Lee Reagan.
and we're talking about convection currents.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
Okay, our focus question is what causes tectonic plates to move? There's a lot of different theories and ideas that have been presented for why the continents are where they are.
The aliens did it.
They haven't moved at all.
And science gives us a different explanation, which right now is convection currents. The tectonic plates have moved over the years to put the continents where they are. Seismic processes are driven by these currents, and they are part of the formation of the magnetic field of the planet.
There are some big forces that we don't typically see every day.
It takes a long time for these processes to become apparent, and only through technology have scientists been able to detect these processes.
So we can break down our original focus question, which was what causes tectonic plates to move, into three new testable questions.
What is the energy source or driving force for convection currents?
How does convection and the driving force behind those currents affect the characteristics of Earth's surface?
How do convection currents move tectonic plates? So we're asking, what is the energy source or driving force for convection currents? We claim that heat from the Earth's interior, or the core, causes convection currents, which we're going to need some evidence to prove this. So what is our evidence? The heat in the interior of the Earth is made up of leftover heat from the formation of the planet and radioactive decay of elements such as uranium. This heat melts material near the outer core, and heating it makes the material less dense and it rises. As it rises, it begins to cool, and when it cools enough, it becomes more dense and sinks back toward the core. This cycle drives convection currents. So how do we know? Well, the Earth's core has a temperature of around 6,000 degrees Celsius, and there's a 2,700 degrees Celsius difference between the outer core and the lower mantle. This heat is what causes the melting of the materials. We also know that the Earth has layers based on understanding seismic waves. There are two types of waves, P and S waves. S waves only travel through solid material, and P waves travel through anything. If an earthquake occurs on one side of the planet, only P waves are detected on the opposite side. This must mean that there is a liquid layer within the Earth. So having this knowledge leads us to a few future questions. What happens in the inner core that converts the P waves into S waves so that we only detect the one type of wave on the opposite side of the planet? And does plasticity affect the speed in which S and P waves travel?
So our next question is, how does convection and the driving forces behind those currents affect characteristics of Earth's surface? Our claim is that heated material caused by convection currents rise to the surface and cools. This causes island chains to be formed. So how do we know? Hotspots are created in areas that are exposed to more direct heat from the mantle. As the plates move, the hotspot remains in the same spot. A new area of plate moves over the hotspot, and new islands can then form. Let's give an example to help our explanation. The Hawaiian island chain formed due to a hotspot. The older islands in the chain are now further away from the hotspot, and their volcanoes may not be active anymore. There is a new island being formed, though, by an underwater volcano over the hotspot. This explanation leads us to ask some newer questions. Have these hotspots always been in existence? Are there other hotspots that are not visible under the ocean? Are there other chains that are not visible without sonar?
Our next question is, how do convection currents move tectonic plates? Our claim is that as semi-molten rock in the mantle is heated, it becomes less dense than its surrounding area and rises. As it cools, it moves under the plates and sinks when it becomes more dense than its surrounding. How do we know? The Earth has an average density of 5.53 grams per cubic centimeter. The crust has an average density of 2.7 grams per cubic centimeter. Therefore, mathematically, the inner layers must have a higher density than the crust. How do currents work with different densities? As the less dense heated material rises, highlighted here in green, it pushes the more dense material to the side, since it can't always break through the crust. As the cooler material is moved aside, it becomes more dense. The motion of this material causes the plates to move. As the material sinks, highlighted here in blue, it eventually reaches the hotter inner layers of the Earth and begins the cycle again. This leads us to ask a few future questions. Are convection currents uniform throughout the Earth? Does the density or weight of various areas of the crust affect the convection currents?
So what have we learned?
Tectonic plates move via convection currents.
Heat from the core drives the currents.
As material heats up, material is less dense and rises.
As it cools, it becomes more dense and sinks.
This creates movement of the plates.
This slide shows everything that we've learned in a graphic. What causes the tectonic plates to move was our focus question. And as you can see, we split that into 3 testable questions. What drives the convection currents? How do the convection affect the surface? And how do currents move the plates? We then split those into further questions to be addressed in the future.
Thank you for listening.
Yay, we're done!